Okay, so today we're going to actually start our introduction to logarithms. And logarithms are kind of they're a big deal. And I did warn you last week, this is not one of those places you want to get behind. It can be a pretty rough thing if you ever get behind on it. So before we do that, let's just review a little bit about exponentials. So first off, do you guys remember what it means to say something is, say, 4 to the third and let's say 4 to the negative third? Let's say, make sure everybody's got those down. What does 4 to the third mean? 4 times 4 times 4, which should be 64. That one doesn't usually bother people too much at this level, but 4 to the minus 3, what happens when you have that negative exponent? This should be a reciprocal, right? So just 1 over 64. Okay, now, let's see if you guys remember this one. Do you remember how to express the cube root of 8 as a exponent? Do you guys remember how to write that instead of in root form, in exponential form? Do you remember what a cube root is? As you're shaking your head that you do remember it. What is that? Correct. That would be 8 to the 1/3. In either case, that number would be 2. Are you guys okay with that? So what would then 8 to the minus 1/3 be? Again, you're saying 8 to the positive 1/3 is 2. So what does 8 to the negative 1/3 mean? That should be 1/2. I'm just kind of playing a little bit with the ideas of exponents, right? So and the reason I'm making a big deal about that and making sure you remember some of those rules. Please remember, what is a negative exponent? It's some kind of reciprocal, right? Also, you want to remember that if you took any value to the 0 power, what is that every single time? These are just some basic rules. What is anything to the 0? Now, what I wonder is how many of you guys know why? Do you guys know why that's the case? Most people don't, honestly. They're like, yeah, because my teacher in Algebra 2 told me that was just a rule, and we go with it. But here's the deal. Do you guys remember what happens if you took x to the m and you divided it by x to the n? What was the rule for division? What was the rule if you take two things with the same base and you divide them? You subtract the exponents. So how is it possible that you got that? Think about that for a second. How is it possible that you got x to the 0? If you started here and you got that answer, what would have to be true about m and n if you did this and you got that? How can you subtract two numbers and get 0? They're the same number. That's why the answer is 1. Because if this was 0, that means x to the m and x to the n were the same thing. What happens if you ever divide anything by itself? You get 1. The only way you get x to the 0 is if you divide something by itself. That's why anything to the 0 is 1, because it only, so if you have 7 to the 0, it means you have like 7 to the 4th over 7 to the 4th. You're just applying that rule. So a lot of people don't understand that. So at least we kind of like threw that one out there for a second. So let's also make sure that you guys remember how to do a little bit of graphing. So let's just say that you were asked to graph y equals 3 raised to the x minus 4 power. Let's just see if we can remember just very, very briefly how to do that. So I generally asked you not to graph the weird function. I asked you to graph the parent function, which would be 3 to the x. How many points did I tell you to graph every time? 3. I asked you to let's graph -2, maybe 0 and 2. And those are not special values. They're just simple numbers that are a little bit spread out. That would give us 9, 1/9, and what was the one in the middle? 2 to the 0, or 3 to the 0, 1, And then remember, y equals 0 is always a horizontal asymptote, right? And so in fact, let's just go ahead and make this something like this. I mean, I don't really care what these numbers are, but what's the story in graphing by transformation? Because we're going to need to know this and know it well for the unit coming up. What do these two things, what does that 4 do? Moves all of the x values which way? To the right 4. And what does it do to all the y values? Maybe it bump them up 7, right? So what's my new horizontal asymptote? Well, it's going to be at 7. No big deal. If we move these up 7, we're going to be right here, and I guess 7 1/9, and it's going to have this kind of look, right? But is this growth or decay, and how do you know? Again, trying to go through a bunch of memory stuff here. Is this growth or decay? What was the rule? Is if that number is anything above 1, because 1 was 100%, right? Is 3 above 1? I think so. So you know the graph is going to look something like that, where we're going to have these 3 numbers, A, B, and C. Of course, I didn't scoot them over like I should have, but I mean, that's the idea, is that you're just going to have those simple numbers every single time. Are you guys all right with that idea? Now, if you have that idea down, now again, sorry everybody, I should have scooted these to the right 4. I kind of forgot that I made them 2, 4, and 6 instead of -2, 0, and 2. So they should be, the axis would be over here. But we've got to start hitting logarithms. So this is a really strange concept to me. There's you guys ever heard of the guy named Napier? Anybody ever heard of Napier? Napier is kind of famous for a couple of things, and one of them was Napier's bones. But he was this astronomer, and astronomers deal with phenomenally large numbers and phenomenally small numbers. Like where would a large number show up in astronomy? Not astrology. We're not talking weird stuff. I mean, astronomy, like science. Distances, things are really far away, aren't they? Like masses of planets, right? There's really, really large values that come, but there's also these little small ones, right? Especially if we're talking wavelengths of light or things like that. They're commonly dealing with phenomenally large and phenomenally small numbers, and frequently you're doing things like distance equals rate times time. You're multiplying, or maybe you're dividing those numbers. And Napier found that it was a little obnoxious. Again, this is before the days of, computers and calculators. So he was trying to come up with a way that could help him efficiently multiply and divide really large numbers easily without having to sit down on paper and go through one of the obnoxious algorithms we have, right? Does that kind of make sense? He's trying to come up with something, and he invented this. Turns out it's really, really useful in math, but it's very, very hard for people, because here's why. So if we start with y equals b to the x, this is going to be an exponential function, right? Exponential function. We know its domain was, do you get from last week, what was the domain of an exponential? What can I allow x to be? X can be anything I jolly well want it to be. If it was positive, it gets big. If x is negative, it's a little tiny number close to 0. But what is its range? Careful on this one. Anything above 0. And so what Napier decided to do is he decided, well, what if we just flip this thing around? And there's sort of a good reason for this. And we have x equals b to the y. Now, unfortunately, now we're kind of stuck, because the idea was, let's flop x and y and let's solve for y. How can I get y by itself? Well, math did not have a way to do that. Enter this idea. Napier said, oh, you know what? That's kind of weird. What we're going to do is we're going to make a definition that says, okay, y is the answer, right? So the answer to this question is the exponent. That's kind of weird. B is the base of that thing. That's weird. All right, we're just going to have to figure this thing out. And he decided he would write it this way. This is the definition of logarithm right here. The definition that y is the log base b. Now, by the way, was b the base of this thing anyway? He just kind of wrote it that way. And that's really uncomfortable to people. I kind of get it. That would make, again, if this is an inverse, what does it make its new domain? Because remember what happens to the domain and range of inverses. They switch places. So my domain had been all reals. My range had been greater than 0, right? So what that means is my domain is now what? Anything above 0, but notice it's saying x's. In other words, in a logarithm, the only thing you can ask for are positives. But your answers can be literally anything you want. So again, doing it this way, that means the graph of a simple problem that is y equals b to the x would look sort of like this, right? Where it would go through 0, 1. And yes, I am assuming right now that this is growth. I could do it as decay. It's no big deal, okay? So we know this looks like this, right? And what does, if b is a bigger and bigger number, it just makes it steeper, but didn't it always go through 0, 1 because anything to the 0 power is 1, blah, blah, blah. Now, this is bizarre. I know people don't like this, especially when they first see it. What do you do when you make an inverse? You take all the x's and y's, and what do we do to them? We switch them. So if, for example, now again, this is not the real value. This could be for anything, but just using nice, easy numbers. Let's say it was 2 to the x. We had 0, 1. We had maybe something like 3, what? When be 2 to the third is 8. We've got this horizontal asymptote kicking out here at y equals 0. Oh, that's weird. We have a point out here maybe at -3 gives me 1/8, right? So let's do the inverse, everybody. What does the inverse become if all the x's become y's and all the y's become x's? So what happened to 3/8? What did it become? 8/3. That's way out here. What did 0, 1 become? 1, 0. What did -3, 1/8 become? 1/3, -1/8, -3 down here somewhere, like this. And y equals 0 became x equals 0, and the graph ends up looking like this. Now, what is very, very, very deceptive about these graphs is, you see how steep that sucker was? What happens if something is really, really steep and then you take its inverse? Is it becomes really, really flat. Something that's super steep becomes something very flat. See, it took me 8 units over here to get a height of 3. How far over, careful about this, for this particular one, how far over do I have to get to a height of 4? Think over here. What happens if I plugged in 4? 2 to the 4th is 16. So I'd have to go 16 units right to get to a height of 4. So if you graph that, literally when you moved 8 units over, you only came up 1. And on the next one, you'd have to go 32 units over to get to a height of 5, and 64 units over to get to a height of 6. Now what Napier did, because he was dealing, like I said, with astronomy, is Napier was actually looking at this one right here. And there's kind of an interesting thing in mathematics where what we're looking at, again, remember y is the answer, but that's also the exponent of the story. So if I was going to write this as an exponent, and what I will tell you is I will usually encourage you guys to rewrite the problem as an exponential instead of a logarithm. In the same way, how did you guys used to divide? Didn't you like do a bunch of multiplication out the side to figure out what would work? But we're going to do the same thing. So you see how b is the base and y is the answer, and I wrote it this way? Well, then according to that, how could I rewrite this? Is whatever that base is, it's going to be the base raised to the y power is x. Sorry about this, everybody, but a lot of you have taken chemistry. But if you ever see log and nobody gave you anything at all, that means it's a 10. Have you guys done that in chemistry? Use base 10? Have you done pH? If you did pH in chemistry, you did base 10, because pH is base 10. And so what that means is, think about it. What would happen if I wanted to get to a height of, say, 3 in the graph? What's 10 to the third? 10 to the third is 1,000. I have to go to the right on a graph 1,000 units to get to a height of 3. How far do I have to go over to get to a height of 6 on the graph? Well, 10 to the 6th is 1,000,000. I literally have to go over 1,000,000 spaces to get it. And kind of the reason I'm mentioning all of that to you is when you look at these graphs, what you're going to find is they look like they're horizontal. But are they growing? They're just growing phenomenally slowly. So this is kind of, let me see if I can get that over here, and let's go ahead and do a new share here for our onliners. So it's going to look like this. So if you are having like y equals 4 raised to the x, that is an exponential, is it not? So if instead I wanted to do y equals log, and I need to get, please quit doing that. I need to get to the controls here a little bit. Maybe it'll allow me eventually if I can get this to the right spot. But what we're going to do is we are going to, where's the subscript? Isn't there a subscript on these things? What's the shortcut on the keyboard? I don't know what it is. Well, put it this way, I'll change this to 10 then. Here is y equals 10 to the x, and if I did y equals log x, it's the same graph flipped across the line, y equals x. We've talked about this before. That's that diagonal weird little line that makes it kind of go hand in hand. So in every single story, what used to be the coordinate, let's say something like, I can't do one very big because the screen is pretty small. If I did 1, 10 on the original graph, what's going to show up on the inverse? 1, 10 is going to go with 10, 1. These are really strange graphs that a lot of people struggle with. But if you looked at that, does that look like it might be going horizontal? I mean, if you go out far enough, does it look like there's probably a horizontal asymptote? It really does. But does it grow? Will it eventually reach a height of 50? The answer is yes, at 10 to the 50th power, which is phenomenally large. Will it reach a height of 1,000? Yeah, somewhere like in Canada on a piece of graph paper. It's going to be so far out there because it's growing. It's the slowest race to infinity you could imagine. It's a really, really, really slow race. But that makes it, this is honestly very difficult for most students to follow through with. So I thought I would give you a few problems right here, and then I'm going to have you help me and to do something else. So we are going to try to take a couple of problems here. I don't know, can you guys see that okay? What I'd like to do is take each of these things and let's just rewrite them as logarithms. So these are right now written as an exponential. Right now, what is the base of the first problem? It is base 8. So this is going to be log base 8. In exponentials, the exponent is the answer. So in number 1, this first problem, what is the exponent? It's a 2. That makes it the answer. And then the 64 is the question. So when you look at that, that's a really strange way to talk about it. Napier was a very, very bright dude. I don't know why he went here. He invented the most complicated thing that you could imagine to do the easiest thing you could imagine, multiply, right? But it turns out it's very helpful in certain circumstances. So if you look at it carefully, this log base 8 of 64 says 8 to the 2 is that. So how would we do this guy right here? It's the log base 10, because the base is 10. It says the answer is -3, but that makes the question 0.001. So what do you think, everybody? Can you handle that? Just rewriting it. The question becomes the answer becomes the question. Oh, this is going to bug you a little bit. Oh, man, I wrote the square root of 49 as 7. That doesn't look like I did anything. Oh, but what's 49 square rooted? We just talked about it a moment ago. That's 49 to the what power? To the 1/2. Ooh, so if that's 49 to the 1/2, can you guys rewrite that as a logarithm? Cooper, you did that really fast. What'd you say? Log base 49. Oh, equals. Okay, it equals 1/2. And what goes right in here? The 7. Nice. Okay, can you do those 3 real quick for me? What's that? Oh, that's 32 to the 1/5 is 4. No, excuse me, that is not true. That's 32 to the 2/5 is 4. Now, wait a minute. Does that make sense? That 32 to the 2/5 is 4? Can you guys break that down for me? Why is that true? Why am I telling you this? It's 4. This is kind of important. You're going to need to be able to analyze that in a little bit. What does the 1/5 do? What is a 1/5 power equivalent to saying? What's that? Not root 5, but the 5th root, right? It's yeah, that's fine. I understand what you're meaning. Root 5 means literally the square root of 5, but you're talking 5th root, right? So what number multiplied by itself over and over and over again 5 times gives you the number 32? You guys understand this too? So what is the 2/5? It says, oh, do that and then square it. Did you get 4? That makes sense, doesn't it? At least I hope. Dakota, can you write this one for me as a log? It's the log base what? Base 5? Log base 3, yes. Of what question? Is 5, because the answer is the exponent. Okay. Monse, what about this one? E. Of is Jolene. H. Log base 32 of 4 is, you guys are, I mean, that's kind of a weird notation, right? So in every single case, remember, what's the answer? The answer is the exponent that we're looking for. Now, all of these, I started here because I think you guys are at least somewhat familiar with exponents, whereas logs are inverses, right? We swapped x and y. That's going to make them a little bit harder. So let's go ahead and start playing with some that are not already handed to you. So I don't know how else to do this other than give you a bunch of examples and kind of work our way through it. So I've got a log base 3. I have 9. The question is, what was the exponent on that 3 that produces the number 9? Who has it? Who's got it? Say it out loud, Stephanie. It's 2. That wasn't a big deal, was it? Because isn't 3 to the 2 9? Now remember, when you look at it, I want you to think exponentially. Is 3 to the 2 9? Okay, Daniel. Log base 9 of 1. 9 to some power is 1. 0. Oh, that was awesome. I like that one. Uh-oh. Crap. The wheels just fell off. This is harder. But I have a hint for you. The hint is this one right here. Think about that one. That's going to help us with this one just a little bit. Because 4 to the 1 would be 4. 4 to the 2 would be 16. It's somewhere between those, but dang, what would it be? How could I take the number 4 and raise it to a power and get 8? 3/5? No. Okay, so let's just for the sake of argument say you don't know. Because right now I don't think you do. Does anybody think you know? 2/3, you're closer. I think it's 3/2. But so let's see. Let's see if you're right. In fact, let's grab a calculator real quick and see what happened here. If we are right, what could I do on my calculator to double check? What's the base again, everybody? Base 4. So the question is it 4 raised to the 3/2 or is it 4 raised to the 2/3? Before I hit enter, what does a half power do? No, what does a half power do? That's all right. What's a half power? It's a square root. That's why I went over that earlier. Half power, what's the square root of 4? 2. And then what happens if you cube 2? What do you get? That should be the right answer. In fact, that was the right answer. Let's keep on going. So remember, sometimes you have to do that. Now, let's just say for the sake of argument that you get into a problem like this and you're like, I'm screwed. I don't know what to do. This is what I do. I call the answer x. So if I rewrote it, would you guys buy that 4 to the x is 8? Are you guys okay if I say it that way? 4 to some power, I got to figure out what that is, right? So this is easy. Isn't 8 2 to the 3rd? Remember, you have to think, everybody, exponentially. So this is 2 to the 3rd, and what is 4 but 2 squared? How is it possible that 2 to the 2nd to the x is 2 to the 3rd is only true if 2x is the same as 3? Don't have a whole lot of room to write here. Do you see how if 2 to the 3 is 2 to the 2x, then 2x and 3, doesn't that make x 3/2? Could we do that? Again, I'm thinking exponentially. Let's go a little bit further. Let's start simple. 2 to some power. Now, again, you may not know, but you could use your fingers. If you need to use a calculator, grab a calculator. 2 to some power is 128. Man. Eight, 16, 32, 64, 7. You guys all right with that? Okay. All right. How about log base 36 of 6? 36 to what power is 6? That's a hint. Not 1/6. Say it out loud, Stephanie. I think you got it. What's that? 2? 36 squared is 6? It's a half. So you guys got to keep in your brain. I mean, I didn't use a half earlier. I did a third. I had Hez give us that third problem before, right? Remember, anytime you're taking a root of something, it's going to be a fraction. That's going to come into play here. Because if you have the log base 81, you should know automatically that 81 is going to get smaller to give you 27, isn't it? So it's going to have to be somewhere between 0 and 1. So what would happen? Any ideas? What kind of root would I want to take of 81? A cube root of 81? Let's see. The cube root of 81, I don't think is very nice. But square root of 81 isn't too bad. That'll give me 9. But let's go a little further. The fourth root of 81. Okay, so that's 81 is 3 times 3 times 3 times 3, isn't it? So what's the fourth root of 81? 3. And what I would need to do is I would need 3 of those. So it should be to the 3/4, right? Because I would want to take that fourth root, but then I'd need to do that 3 times to get that 27. So again, could we do it like we did up here and said, well, 27 to some power is 81. That's 3 to the 3. Sorry about the penmanship there. That's 3 to the 4th. My paper moved on me. So anyway, so you can see that 3x is 4, and we've got that. So I got a couple for you to try right there, right here. I think I designed this thing to actually go the other direction where the problems are easy this way and they get harder as you proceed to the right. But anyway, see if you guys can come up with which ones work there. And then I'm going to have you guys do something with delta math for a little bit. Just have you play with these just a little. All right, first one. 5 to what power is 125, everybody? 3, that was not too bad, right? By the way, can you check all those on a calculator pretty easily? Just poke them in to see. Anybody at 27? 27 to some power is 3? Any ideas? A third, yeah. The cube root of 27 would be 3, that's good. Now we got into something kind of weird. So again, what I do is I think of like 9 and I think of 243, and I know that they have the number 3 in common. Think about that for a second. Do you guys see how 9 has a 3 in it, doesn't it? Does 243 have a 3 in it? So this is going to be kind of strange. Let's see if you guys can come up with it. But there's something else. This is the first one I've done this to you. I made it a fraction. What does that fraction mean? It's going to be a negative exponent. So remember, the answer is the exponent. So the answer is going to be negative in this story. So we know that. How are you going to turn a 9 into a 3? And you got to understand, why do I want to turn it into 3 is that's what they have in common. How do you turn a 9 into a 3? Not a cube root, but a 1/2. Yeah, it's going to be a square root, right? So I know I've got a half in there. So I'm guessing that I might be going too fast here, but remember we said we could do this. So let's try it that way. Would it be okay to call this 9 to the 2x, 3 to the 2x? Is that 9? Is 3 to the 2 9? Let's see if you could help me with this one. What the heck is 243? How many 3s is that? It's 5 of them, but has said it was negative, wasn't it? Now, if you look at it that way, can you tell me what the answer is? 3 to 2x is 3 to the minus 5. What does x have to be? It has to be negative 5/2. That's really, really strange. So according to this is kind of strange. If I did this right, if I took 9 and I raised it to the negative 5/2 power, what should the answer be? It should be 1 over 243. Now, the 1 over, in fact, let's do this. Let's just take this off. So if I did this, I should get 243. So does it make sense that it's 1 over that? Because I had that negative exponent. So what I want you guys to try today, and I have not done this with you guys yet this year, is I'd like you to go to deltamath.com. Okay, go to deltamath.com. 764449. Now, Delta Math has some similarities to the whole Google suite of stuff where you're going to put a code in. But Delta Math is a little bit different in that you actually put in your teacher code and then you have to click which class you're in. And I put in a simple assignment where there's 5 questions that are very, very basic logs. Just see if you can evaluate them. 5 questions that are a little more advanced logs, and then 5 questions that are a little bit more advanced logs. So I would like you guys to try each of those for just a few moments. I'm going to watch what happens when you do that here in just a moment. So I have a couple of quick questions to kind of remind you of something, and then I wanted to go over the graph just briefly, and then I'll give you the major assignment. So can you guys tell me how literally to take 8 to the 4/3 power? What would that mean to do? In order of operations, what do you think you would do, Asa? You would, 8 to the 1/3 would be 2, because the cube root of 8 is 2. And then what does the 4 do? That 2 times 2 times 2 times 2, that would be 16 then, right? Okay. Now, the reason I said that way is that I wanted you to then think about how can I rewrite that as a logarithm? This would be the log base 8 of 16. Now, before I keep going, you know what the answer is, but think about it. Why is the answer to log base 8 of 16 4/3? Why? Because the cube root of 8 would get me all the way down to the number 2, and could I manipulate the number 2 pretty easily to produce the number 16? Okay, how about this one? What about 81 to the negative 3/4 power? What's a 4 do? That's a 4th root. So what number times itself 4 times would give you 81, everybody? Is it 3? So so this is going to get me down to the number 3 as the base, right? And then what am I going to do to that 3 is we're going to raise it to the 3rd power, which would be, what's 3 times 3 times 3? 27. What does the negative do then? It is, oh, that's so obnoxious, isn't it? Isn't there a lot of thought process you have to go through? It's honestly like trying to do a Sudoku in your head the whole time. You got to keep all these little bells and whistles, which means you got the log base what? 81 of the number 127. Now pause for a second. What's the connector between the numbers 81 and the number 27? What connects 81 and 27 together? The number 3. So if I could turn this one into a 3, this would be 3 to the 1/4, right? So that's my 1/4. And then 3 to the negative 3 would do that, and that's where the negative 3/4 comes from. Which means if I had the log base 16, oops, you wrote that down already, you know what it is. What is the connecting value between the number 16 and 32, everybody? What would connect 16 to 32? Ooh, is 16 is definitely a power of 4, isn't it? Is 32 also a power of 4? No. So let's not go with 4, let's go with 2. So I want to think of the family of 2's. So how would I get a 16 all the way down to a 2? What kind of root is that? It's a 4th root. So now how do I get it back up to being, so 16 to the 1/4 gives me 2. How many 2's does it take? It takes 5. So could I check this answer? If I was taking a test, how could I check to see if I did this right? What's the base? Base is 16. I'm telling you the exponent is 5/4. And what should the answer therefore be if I hit enter? Is it better be 32? So I think of these problems, and again, I understand that a lot of you don't have this experience to think in this way, but what I want to do is I want to try to see if I could get you to think about these numbers. And you probably, again, don't have a heck of a lot of experience thinking about exponents. But I will tell you, when we play with them, you're going to see a lot of 2's, you're going to see a lot of 3's, you'll see a few 4's, you'll see very little above about 4. So, have you guys ever seen the number 32 a few times in your world? What is 2? What is 32? How could you get 32 using an exponent? Well, I can't multiply a bunch of 3's and get it. I can't use 4's to get it. How many 2's does it take to make 32? It takes 5 of them. So how do I take the number 32 and get it all the way down to the number 2 is I need a 1/5. Now, how do I get it back up to 128? How many 2's would it take to get to 128? Got to think exponentially. What's 2 times 2 times 2? How many does it take to get to 128? 7 of them. Got one more thing that went wrong. Because I didn't ask you for the number 128. What did I ask you for? How do you make a reciprocal in exponents? It's going to be this. Now, the one thing that I did not get into with you guys yet is if you ever see LOG, that right there is called common log. You should write this down. Make sure you have that down. This is the normal thing. On my calculator right here has a button that says LOG, right there, log. That means it's going to be base 10. This is the one place in life where an unwritten value automatically is the number 10. Usually an unwritten number is the 1, right? But a square root, if we don't write anything in the little hole, it was a 2, right? So we have some unwritten rules here and there, but logs should be base 10. However, if anybody other says this one right here, in other words, if they say log of x is y, that means x is 10 to the y power. If they ask you this one right here, that's LN, that stands for log natural. It comes from another language, which is why it's kind of written backwards. You know how like Spanish sometimes are backwards, how we write things? Same thing here. if you say log natural, it's one of the things that I gave you a hint that real life problems don't deal with other kind of bases, they deal with the base e. So what this is x equals e to the y. Okay? So in your work that you're going to do in the homework, and I am choosing to slow it down a lot off of what I have on my plan, is if they were to ask you to graph this and they were asked you to graph this, I do need to make sure you're aware of it, and then we'll talk about some of the bells and whistles. So if you were asked to graph this, this is how I would encourage you to do it. Are you guys good at logs yet? No, but you're probably okay at exponentials. So what I would tell you to do is, what's the base here? If it is as log, 10. So that means 10 to the y is x. Let's make an input-output table. Now in this case, is it easier to plug in x to get y or y to get x? Look right here. Is it easier to plug in x to get y or y to get x? Oh, y to get x would be a lot easier, wouldn't it? So let's think about it. What would be a smart number for me to plug into for y? I think 0 would be a phenomenally nice answer, because anything to the 0 power is 1. Do you notice I'm doing this backwards? Isn't that kind of weird? Well, I told you I like to spread things out, but these are going to get big really, really fast. What if I made y 1? That's pretty spread out, isn't it? What's the other value I might try? -1 would give me 1/10. So the graph is going to have this vertical asymptote at x equals 0. It's going to cruise up here like this, and it's going to be extremely steep, and it's going to have values of a, b, and c, where a is out here at 10,1, b is at 1,0, and c is way down here at 1/10, -1. And the same thing's going to happen over here, and I'm going to write x is e to the y, same as I did before. I know you're not going to like this, but it is what it is. I'm going to make different numbers for y. Notice I'm going backwards, aren't I? Why am I going backwards? Because it's an inverse. Inverses go backwards. So what does 0 give you? What is e to the 0? You guys need to know that. What's e to the 1? E. 2.718, yeah. And what is e to the -1? Well, 1 over e. Which again, this is about 2.71. This one's about 0.3-ish. So if I go over here to graph it, no big deal. I still have my vertical asymptote at x equals 0. It still goes through these values. It's going to be in here, A, it's going to be here, it's going to be in here, and it's going to again be kind of a shallowy looking graph. But without taking much time to do this, in your homework, what would happen then? I'm going to keep this as brief as I possibly can. What would you tell me to do if they asked me to graph this? Would it be that very graph with all of its bells and whistles moved to the right 5? Guys cool with that? Okay. What if I said, let's do this? Is the 2 inside the log? No. Is the 7 inside the log? No. So it's only going to take the y values, it's going to double them all, and then what? So it's going to stretch it vertically a little bit and then scooch it up. Is it the same thing we've done before? So if you know this one, can you graph anything you want? This one I hate. Oh my gosh, this one kills me. What about the log of 4 minus x? I warned you about that. Never let anything be attached to x, right? So we got it. So we have to rewrite it a little bit. And what are we going to do to that 4 minus x? Is I'm going to make it a negative, and then, but what does that do? Really important. We're going to first take this negative. What's it going to do? It's going to flip it across the X or Y axis? Going to flip it across the y-axis. So instead of going this way, it's going to go the wrong way. So now my domain is actually now negative numbers. And then what's that going to do? Move it to the right 4. So that means my vertical asymptote is going to be at 4. Now the vertical asymptote on these always is easy. Just look at the inside and where it would be 0 is your vertical asymptote. Which means if you know what this one works like, can we move it around too? We can move it around at will, because every graph is going to be this graph, just manipulated a little bit. So in your textbook, you're going to go to 3.3. I'm really trying to advocate for you guys. I'm going to go slow. I'm going to figure out what I'm going to cut out later to do this, because I really should have a second lesson, but I don't think you guys are ready for that, having never seen this before. So you guys are going to do 1 to 24 all. I hate assignments that are like that, but what they are, this is very much like the little delta math thing that you did. You're just going to look at some problems, but what they added in those problems is some E's. So you're going to see some LNs in your work, okay? And then you're going to skip up and you're going to do a few problems, and I figured I would go 27 to 60. And if I ever do that, that means multiples of 3. So that means you're going to do 27, skip up to 30, skip up to 33. Reason I do that is in most textbooks, they're written in chunks. And if you do multiples of 3, you'll do 1 or 2 problems of any style. So there's a graph, and you'll do 1, maybe 2 graphs that are log base 10. And then you'll do 1, maybe 2 graphs that are log base E. Odds, you're going to do a lot of them. This way you do 1 or 2, and then you move on without kind of feeling a little frustrated. Also, you get half of your problems, you can check your answers in the back of the book, and half you can't. So on your calculator, there are some problems that go like this. This is kind of silly, but I better mention it before I say go. If they said, hey, what's the log of 73? Now, honestly, if I said log of 73 and I didn't give you a base, what base is it? If I just say log of 73, it's 10. But you know what? I don't know what 10 to some power 73. That's not nice, is it? You're not going to have one of those memorized. I know 10 to the 1 is 10. 10 to the 2 is 100. So somewhere between 1 and 2. So I just hit log 73. There it is, 1.86. Yay. Move on. Okay. So there's a few problems in there, in this set, where they literally just want you to grab a calculator and see if you can use a machine. And if I say, hey, what's the natural log of 135? Fine, the natural log of 135. I hit enter, there it is. They just want to make sure you know how to hit some buttons and where to find them. If you're looking for where is the log base 7 button on your calculator, mine doesn't have it. A lot of yours does. I'd rather you not use it. I'd rather you learn how to do these problems without it, but after you've practiced a little bit, I could probably share it with you. Okay, so you guys know where to find your book? Fin Classroom. I stored it for you. So it's page 308 of your textbook, theoretically. So that's kind of where I'm going to stop for today. You guys have about 15 more minutes. Can you go to the textbook? Don't worry so much about the delta math now. Go to the textbook and start working on those. Page 31 of the online. Perfect. Thank you much.